Hi, I'm Erfan Khaniki, and I'm going to talk about jump operators, interactive proofs, and proof complexity generators. One of the ultimate goals in proof complexity is proving superpolynomial lower bounds for any propositional proof systems, uh, which by Cook-Recko theorem is equivalent to NP is not equal to QNP. Unfortunately, we are very far away from that goal, and we cannot prove superpolynomial lower bounds for a strong enough proof system such as AC0 parity, Frege, extended Frege, and etc. Uh, there are two main problems that prevents us to prove lower bounds for a strong proof system. The first one is lack of methods, and the second one is lack of candidate hard formulas. There are three main categories of hard formulas that experts believe they should be hard for any kind of proof system. The first one is random formulas, such as random DNFs with suitable densities. The second one is proof complexity generators, which I'm going to define very briefly. Suppose G is a function in that can be computed in polynomial time, and assume that G on inputs of length n maps a strings of length n to a strings of length mn, in which mn is bigger than n. Then we say that G is a hard proof complexity generator for P if P requires super polynomial size proofs of the formula tau bgn for any B. And tau bgn says that B is not in the range of G. As G is a stretching map, there are B's which are not in its range. So like tau bgn is a tautology for some B, and it's a meaningful formula. And the last kind of formulas that are believed to be hard for any proof system is finite consistency formulas or finite reflection principles. Finite consistency formula says that for any x, for any fixed x, it says that P does not have proof of length at most x for contradiction. And the reflection principle formula says the usual soundness in propositional logic, namely that if pi is the proof of phi, then phi a should be 1 for any assignment a, but the finite version of it. Krajcek and Pudlak conjecture that there is no optimal proof system, which is equivalent to the statement which says that for any proof system P, there is another proof system Q such that P doesn't have short proof of finite consistency of Q. So this conjecture says that, in particular, says that there is a jump operator J in the lattice of propositional proof systems, such that for any proof system P doesn't have short proof for the consistency of JP, or equivalently, JP cannot be simulated by P. So the natural question here is that what is the complexity of J? So unfortunately, this conjecture doesn't say anything about the complexity of J. So for example, is J computable? Because if it's computable, then we can use it to produce hard formulas for any kind of proof system, let's say for extended Frege. Some candidate computable jump operators were proposed by Bas, Krajcek, and Pudlak, and Krajcek. So let's see at Krajcek's jump operator, which is called Krajcek's implicit proof system. Let P and Q be two propositional proof system. Then the pair P and Q is a Cook-Recko proof system, and it can be defined as follows: a P and Q proof of a formula phi is a pair pi and C, where C is a circuit, such that pi is a P proof of the canonical 3DNF, which says that correct 3DNF corrects CQ phi, where correct CQ phi is a tautology if and only if the truth table of C is a Q proof of phi. So in this definition, Q gives the actual proof of phi, but it gives it implicitly by circuit. And P has the role of verification that this implicit proof is actually a real proof of phi. So here we can replace P with other forms of verification. For example, we can use interactive proofs. In particular, we can use the sum check protocol. So what is the sum check protocol? The sum check protocol is an interactive, randomized interactive proof that is describing in the interaction between a limited power verifier and an unlimited power prover, and they know 3CNF phi in n variables. And the goal of this protocol is to see whether phi is an unsatisfiable CNF or not. And they can do it in like n rounds as follows, which I'm not going to describe. And the important point about the sum check protocol is that it has soundness and completeness. Namely, if phi is an unsatisfiable formula, then there is a prover which, with probability 1, can persuade the verifier that phi is unsatisfiable. And the soundness says that if phi is not unsatisfiable, then for any prover, verifier with high probability realizes that the prover is lying and phi is not unsatisfiable CNF. So as we look at the protocol, the prover does some very complicated computation. So we cannot put like the prover movements directly into this definition of IP and Q jump operator or proof system. But we want to make like Cook-Recko proof system or something close to Cook-Recko proof system. So we cannot use sum check directly. So we do as follow. So an IPQ proof of a formula phi is a tuple P, pi, C, and C prime, where P is a prime number, pi is a Pratt certificate for P, and the role of P is used in the sum check protocol, where the prover is going to work, and the prover and the verifier are going to work over FP. C and C prime are both circuits. C encodes the movements of the prover in the sum check protocol when the input formula is correct C prime and Q phi. And this is the definition. So from this definition, we can see that IPQ is actually a Merlin-Arthur proof system. So it's like an IPS proof system. And this definition can give us like IPS proof system for any proof system, for any Cook-Recko proof system. So what we can say about this kind of proof systems. So what is the relationship of this kind of proof system to the usual Cook-Recko proof system? So the first theorem clarifies this. This is just for implicit version of IP and EF, but it can be proved for any proof system P. So the theorem says that if implicit extended Frege, which is the pair of EF and EF, can prove hard on average exponential size circuit lower bounds, then IEF simulates IPEF. And so here we want to prove this theorem. At least we want to gives some ideas that how one can prove this. So the proof idea is as follows. So we know that if P is strong enough and P can prove reflection principle for proofs for another proof system, then P simulates P prime. Namely, if P prime has a short proof of a formula phi, then P also has a short proof for that formula too. So this means that our goal is to prove that implicit extended Frege can prove the reflection principle for IP and EF. So, but IP and EF is an MA proof system, so we have to define its reflection principle. So the naive idea is the following formula. So it says that for every phi, for every pi, and for every A, if pi is a proof of phi, but here we cannot use a polynomial time function because this is an MA proof system, so the verification part is randomized. So if pi is a proof of phi with high probability, which makes it a real proof for phi, then phi A equals to 1. But we need to write these things in the propositional language. So the probability part is too big because we have to enumerate over all possible R's. So, and this becomes exponential, and we can't use it for our goal. So instead, we use approximate counting, Revier's approximate counting, which is based on Nissan-Wigderson generators. So the formula is the following. The reflection formula can be defined as following. For every phi, for every pi, and for every assignment A, and for every Boolean function f, if f is hard on average for exponential size circuits, then this probability, which says that pi is a proof of phi in IPEF is true, then phi A equals to 1. But here, the difference is that we don't use the real probability. We use the Nissan-Wigderson based on F to write this probability. And this whole formula becomes succinct, and we can use it to prove our theorem. But this formula, as we can see, is very complicated. So, and IEF is also very complicated. So it's hard to work on this formula in IEF. So we use a bounded arithmetic corresponding to IEF. So S12 plus 1x versus IEF is the same as S12 versus x-net Frege. And S12 plus 1x corresponds to exponential time reasoning. So what we can show is that, first of all, S12 can prove the soundness and completeness of the soundcheck protocol. And this implies that S12 plus 1x, first we can show that S12 can prove soundness and completeness of the soundcheck protocol. And this can be used to show that S12 plus 1x can prove the reflection principle for IPEF. But reflection principle for IPEF, as we saw here, it has this hard F, and therefore it's not a for all pi b1, it's a for all sigma b1, or it's a TFNP problem. So we cannot work with its translation in implicit extended Frege. So we need a propositional proof system Q that can work with sigma Q tautologies, which are corresponding the propositional translation of the TFNP problems, such that IEF versus Q versus S12 plus 1x is the same as EF versus G1 star versus S12. To this end, we use the TFNP characterization of S12 plus 1x. So we know that there is a TFNP problem which its totality can be proven in S12 plus 1x. And moreover, any TFNP problem that can be proved total in S12 plus 1x, there is a reduction between this problem and the other problem that I mentioned, and this reduction can be proved in S12. And we can define our proof system GIF as G1 star, which is the quantified propositional proof system corresponding to S12 plus the propositional translation of this TFNP problem. And this proof system has the required properties that we needed to prove the theorem. And here's the sketch of the proof of the simulation. So first of all, we know that IEF can prove hard on average exponential size circuit lower bounds for Boolean function f. We know that IEF and GIEF are the same over propositional tautologies. And we know that S12 plus 1x can prove the reflection principle. This means that GIEF can prove the translation of reflection principle efficiently. And moreover, we know that GIF can prove the probability part of the reflection principle for the specific formula phi, because we know phi, we know f, and we know pi. So this whole thing becomes a propositional formula without any atoms. So using mode exponents, we can get that IEF can efficiently prove phi. The next application is about hardness magnification. So we can define a lower bound formula for IPP proof systems, namely the formula, LB formula, it says that there is no IPP proof of phi of size at most m. And this formula is true if hard of f is true and phi doesn't have a proof of size m in IPP. And the hardness magnification says that if P extends Frege and Q extends Dirichlet resolution, then, and moreover, if P doesn't have short proof of any circuit lower bound, polynomial circuit lower bounds, then there is no sub-exponential size P proof of the LB formula where n is the size of the LB formula, when phi is a tautology. The LB formula is complicated, so it's hard to work with it directly. Instead, we use non-standard models of arithmetic to work in it. And the reason is that we have the following feasible completeness and soundness for proving lower bounds. Namely, if we have a strong enough proof system and the following statement holds, that if there is a non-standard model where S12 plus consistency of P plus the form with the plus the sentence which says that psi is not tautology holds, then P doesn't have short proof of psi. On the other hand, if P doesn't have a short proof of psi, then such a model exists. And the reason that we need to go to non-standard models or these imaginary objects is that if psi is a tautology, then it always has a P proof. The proof might not be polynomial size. So we cannot find a falsifying assignment or force a falsifying assignment for it. And how the proof goes. So we know that phi is a tautology. So there is an exponential size tree-like resolution refutation of negation of phi that can be expressed by a small circuit. Like if the proof is the canonical tree. So this means that correct of C and tree-like resolution of negation of phi is actually a tautology. This means that there is a prover by the completeness of the sum check protocol that can persuade the verifier that correct of C tree-like resolution of negation of phi is a tautology. And the movement of the prover can be encoded as strings of exponential size in phi. On the other hand, we know that P cannot prove any polynomial size circuit lower bounds. So by feasible completeness, we get that there is a non-standard model of S12 plus consistency of P plus the statement which says that phi prime has a small circuit. So in this model, we know that C and C prime is an IPQ proof of phi of polynomial size, which means that in M prime, LBQ has a falsifying assignment. So by feasible soundness, P doesn't have short proof of LBQ. And other applications of these jump operators are the following two theorems. The first one is a barrier for proof complexity lower bounds. It says that if there is a generator G that is exponentially pseudo-surjective for extended Frege, then S12 plus the sentence which says that IP and tree-like resolution is a sound and polybounded proof system for true DNFs is consistent. Pseudo-surjectivity is a type of hardness for proof complexity generators, which I'm not going to explain, but I will give a model theoretic explanation that what it means. And another point is that S12 is very strong from the point of view of metamathematics of complexity theory. For example, it can prove PCP theorem. So this barrier is actually a strong barrier. But the assumption should be true so we can get this barrier. And Krajcik actually conjectured that pseudo-surjective generator for extended Frege should exist. So this assumption is not something unreasonable. And here's the proof idea. So if G is exponentially pseudo-surjective for EF, then there exists a model of S12 plus the sentence which says that any Boolean function can be computed by a small circuit. So exponentially pseudo-surjectivity implies this the existence of a small circuits for any function in a model. So we can use the proof of the hardness aggregation and the fact that S12 plus 1x can prove the reflection principle for IP tree-like resolution and get the result. And the last application is about automatability and feasible disjunction property for extended Frege. The automatability is a property which says that there should be an algorithm that runs in polynomial time in the shortest P proof of formula phi, if phi is a tautology, and outputs a P proof of phi. Feasible disjunction property says that if P has a short proof of phi or psi where phi and psi doesn't have any common variables, then either P has a short proof of phi or P has a short proof of psi. And the statement says that if there is no P-poly natural property useful against P-poly, then either EF is not automatable or intuitionistic S12 doesn't prove a strong reflection principle for IP tree-like resolution. The second statement says that if NP-poly natural property useful against P-poly do not exist, then EF does not have feasible disjunction property, or intuitionistic S12 again cannot prove a strong reflection principle for IP tree-like resolution. And experts believe that P-poly natural property and NP-poly natural property useful against P-poly do not exist. So the assumptions here are not unreasonable too. Finally, we looked at the general theory of jump operators. It is widely believed that computable jump operators in proof complexity should exist. On the other hand, Pudlak conjectured that for every finite axiomatizable true theory T that extends S1 to, T cannot efficiently prove finite consistency of T plus con T. And we prove several statements in this regard are equivalent, including the following ones. Namely, there exists a computable jump operator in proof complexity. And the second statement is that for any strong enough finitely axiomatizable true theory T doesn't have short efficient proof of finite consistency of T plus Conti. Namely, the weaker form of Pudlak's conjecture is equivalent to the existence of jump operator in proof complexity. There are some other things that were discussed in the paper, namely a new hardest property for proof complexity generators, a definition of another jump operator based on the PCP theorem, and a new types of TF20 problems motivated by the definition of reflection principle for IP and P that we call them small circuit problems. Here are some open problems. The first problem asks whether if Q can simulate Q prime, is it the case that IPQ can simulate IPQ prime? We know that this is not the case for Krajcik's implicit proof system. What about here? The second question asks whether we can prove the reflection principle for IP tree-like resolution in a weaker bounded arithmetic. Namely, can we prove it in T2? And the last question, which is probably the most important question here, is whether there is a computable jump operator in proof complexity. Thank you.